Hello? Maji? Eki? Ogambye ki? Siwulidde. Okay. Ennaku zino ng'otwala nnyo amatooke. Tulinawo ye y'ogumu ekitundu. Hello. Gwe Mukasa. Hello? Mbeera wano mweza sirika. Good afternoon, everyone. Good afternoon, guys. Hello. Hello. Can you hear me? We have a new definition today I want to share before we can proceed with any calculations. And that definition is called surface energy. By definition, surface energy is the work done in enlarging a surface area of a liquid by 1 meter squared under isothermal conditions. Whereby isothermal conditions are conditions where we have a constant pressure, a constant temperature taking place. So we have a constant temperature in regard So if you do work in enlarging a surface area of 1 meter squared, the liquid under a constant temperature, then you are doing what we call surface energy, or the work you do it against surface tensional forces. So whereby surface energy is given by gamma times cross-sectional area. So if the surface is circular, then the area is pi r squared times gamma. So this would be the expression for surface energy, or energy due to gamma. So energy due to gamma is always pi r squared gamma. So with that definition, they can ask you, for example, like, I check the work done. I check the work done against surface tension, against surface tension forces in blowing a soap bubble if its radius is increased from 2 centimeters to 3 centimeters. So in this case, the work done against surface tension surface tension is equal to the change in area times the coefficient of surface tension gamma, whereby this energy going to be got from area 1 minus area 2, that is the change in area, times gamma, which is going to be equal to pi r1 squared minus pi r2 squared, where r1 is 3 centimeters and r2 is 2 centimeters. So we shall get the energy from pi into r1 squared minus r2 squared times gamma. Gamma for water is 0.07. I think I forgot to, for soap, gamma is 0.07 Newton per meter. So if I substitute, I'll have 22 over 7 into R1, which is 3, 10 power negative 2 squared minus 2 times 10 power negative 2 squared times 0.007. Can you press your calculator and give me the answer? Press your curve and get the answer. I'm waiting for you to reply.
One 1.1 exponent -5.
These are jaws. Eh? Are you sure it's 1.1? No. This gamma was not, this 0 was not there. It is just 0.07. So can you try it again?
Teacher,
Yes, please.
1.1 times 10 power -4.
1 point.
Power -4. 1.1.
Ah, there is one other thing we have forgotten. We are dealing with a soap bubble, not so? Gamma for soap bubble is 2 gamma, not so? So I forgot that too. Gamma for soap is always 2. So you multiply by 2, the answer is 2.2 exponent -5. That is the answer. I don't know that it's raining at your side like mine, but I hope you can hear me. So that is the answer. Then the last idea in this case is what we call combined bubbles, or what we call coalescing bubbles. I have a bubble 1, radius R1, it combines with another bubble R2 of radius R2. Then these 2 bubbles form one combined bubble, radius big R. What time is the lesson? Fatuma, which lesson are you talking about?
Teacher, this lesson, it starts at 3:30 on
Yeah, it starts at
timetable.
3:30, but I was having a problem. I'm in my garden, so I had no network. I was down in the swamp. I had to climb to a hill. Right now I'm in a hill. So it
Okay,
took me
teacher.
some time. Yeah, sorry for that. So the work done in blowing the big bubble, in getting the resultant bubble, work done in blowing the resultant bubble, in blowing the big bubble is equal to energy stored initially, is equal to the energy stored initially by the 2 combined bubbles. By the 2 combined bubbles. So if you're looking at this work done in blowing this resultant bubble, it is equal to the energy we had before when these two bubbles had not yet combined. So in that case, the change in the area times gamma gives us the work done in blowing the resultant bubble. Now for the individual bubbles we had area 1 times gamma of the smaller bubble. Let me wrap this out. So we had area 1 times gamma plus area 2 times gamma. So the big area which we have acquired now has an area of, which is the change in area. I've called it change in area. It is pi big R squared. So the area of the circle is pi R squared. So I'll have pi big R squared times gamma is equal to pi small r1 squared times gamma plus pi small r2 squared times gamma. Because everything has gamma, we can lose the gamma. Everything has pi, we can lose the pi. When you lose the pi, we shall realize. So finally, we shall have r big squared is equal to r1 squared plus r2 squared. And this is the expression for finding the radius of the resulting bubble when the two bubbles have coalesced. So therefore, if I want to find r alone, I will say r is the square root of r1 squared plus r2 squared. So we can as well go ahead and get the excess pressure in the resulting bubble. So excess pressure in the resulting bubble because if this bubble is a soap bubble, then we know for a soap bubble is 4 gamma out of the radius. So it will be 4 gamma out of the radius r, which is big. This is the change in pressure or the excess pressure. So you first get this big R of the resulting bubble, then you substitute it in this formula for excess pressure, and then you can be able to attain the radius of the resulting bubble. Titus, your hand is up.
Teacher, I was asking you to please back up.
Pardon?
I was asking you to please back up.
Yeah.
This where we
I can't hear you well.
A gamma is equal to. Teacher, if you could please back up to where we have A gamma is equal to A1 gamma plus A2 gamma.
Where we have what?
A gamma is equal to A1 gamma.
Okay.
Plus
Having seen that surface energy, you know energy is work done, okay? Having seen that surface energy is given by gamma times cross-sectional area, so the surface energy or the energy I do or the work I do in combining this bubble or the energy which this bubble initially had was its cross-sectional area 1 times the coefficient of gamma. The energy this bubble had was cross-sectional area 2 times what? Gamma. When you combine these two, the initial energy we have because of energy conservation should be equal to the energy possessed by this new resultant bubble formed, whereby the resultant bubble has been formed as a result of change in the area times gamma, which area is now given by pi big R squared times gamma. So the energy we have here for the resultant bubble is equal to the energy we had before from energy conservation. So total energy you had before should be equal to total energy you have after. We are assuming that all the energy is used in blowing the resultant bubble. We do not have any energy wasted at any one point. If we had energy wasted, the bubble would cease to exist. It wouldn't be able to exist because some of the energy would have been lost, or it would be having a smaller radius. So the reason why it has a bigger radius is because we have maintained, we have conserved the energy we had before that we have it up. Any other concern? Now, that is if the bubbles have coalesced. That was Roman 1. Coalescing means they have been merged together to form one bubble. Then there is another situation where the bubbles do not combine to form one bubble. But what they do, they just touch each other and they lean against each other. There we say they have combined. While if they form one resultant bubble, we say they have coalesced. So, in that case, the first one, we have had coalescing bubbles. Now we are going to have combined bubbles. So case 2, combined bubbles. Bubbles are combined if and only if they are of this form. You have a bubble of radius R1 combining with a bubble of radius R2. Then the resultant, they do not merge, but one gets stuck onto the other. Okay? So the reason why this one has expanded is because this one has pushed it in. So if this one exerts a pressure inside of P1, then even here on this wall we shall have a pressure P1. Then outside we shall have atmospheric pressure. Then inside here we shall have a pressure which is P2. Even inside here we shall have a pressure P2 due to the second bubble. But outside here there is atmospheric pressure. Now we need to get the change in pressure at the interfaces, at the different interfaces. So if the bubbles do touch each other, they can ask you to show that the radius of curvature of the common interface, the radius of curvature is here. That is the radius of curvature of the common interface. They can ask you to show that the radius of curvature of the common interface is defined by big R is equal to R1, R2 all over R2 minus R1. So that is what we are going to prove. Now, in bubble 1, consider bubble 1. Here at the point of contact with bubble 2, firstly, the pressure inside seems to be greater than the atmospheric pressure because it is curving towards where the atmospheric pressure is. So it would be P1 to overcome the atmospheric pressure to give us the force due to surface tension at the interface. Because these are soap bubbles, so the force due to surface tension will provide a pressure gradient, which is 4 gamma out of R1. This will give us equation 1. When you come to bubble 2, bubble 2 has this interface right here. This one. At that interface, pressure P2 is greater than pressure outside. So the change in pressure will be P2 minus H is equal to 4 gamma over R2. While at the interface, we have a change in pressure, which is P1 minus P2. Why is P1 greater than P2? Because you see P1 has curved into this pressure P2, P1. It means it is pushing it inside, so it's a great pressure. Even you can use common sense of pressure, where we have the cross-section area being smaller, we have a very big what? Pressure. So small bubbles have a higher what? Pressure than big bubbles. So the pressure in P1 is greater than the pressure in P2. So the change in pressure at that interface will be equal to 4 gamma out of the radius of curvature. But remember, this was equation 2. This can become equation 3. So if I subtract Roman 1 minus Roman 2 what am I going to realize? I'm going to realize P1 minus P2 is equal to 4 gamma over R1 minus 4 gamma over R2. But we have realized that the change in pressure P1 and P2 is the 4 gamma over big R. So 4 gamma over big R is equal to 4 gamma out of small r1 minus 4 gamma out of small r2. When you divide this by that, we shall lose all the gamma. Consequently, you can divide everything by 4, and we shall lose the 4 here, lose the 4 there, lose the 4 there, and we shall remain with 1 out of big R is equal to 1 out of R1 minus 1 out of R2. When you simplify this, you're going to attain 1 over big R is equal to, when you cross multiply, R2 minus R1 divided by R1, R2. On cross multiplication, we can make big R the subject, which is R1, R2. What is over R2 minus R1? And this is our expression for the radius of curvature of the common interface, whereby we have two bubbles that have just been combined. They have not coalesced to form one, but they're just attached to each other, one pushing in the other. So the radius of curvature of the common interface can always be deduced from that equation. Questions before we go to examples? Any questions before I bring in an example in this category of combination of bubbles? Okay, if no questions, two soap bubbles. Red eye, 2 centimeters, 4 centimeters, coalesce, respectively, under isothermal conditions. the surface tension the soap solution is 2.5 times 10 power negativity of 2 newtons per meter. Calculate the excess pressure inside resulting bubble. Now, the bubbles are coalescing. If they are coalescing, if the question comes like this and is more than 3 max, you derive this equation. Then you work out. If it is just 3 max, then first get big R by identifying R1, which is what? 4 centimeters. R2, which is 2 centimeters. So big R will be equal to square root of R1 squared plus R2 squared, which is going to be square root of 16 plus 4, which is root of 20, which is the same as 5 root of 2. Sorry, the same as 2 root of 5 centimeters. But because we are going to find pressure in terms of pascals, we need to convert it to meters. So excess pressure, remember, is given by what? It's given by 4 gamma out of big R, which is 4 times gamma, which is, because it's already soap, that's why we have the 4 times 2.5 times 10 power negative 2 divided by 2 root of 5 times 10 power negative 2. I can divide off the exponent negative 2, and I'll lose this with that. When you press the calculator by 2 once, by 2 twice, you shall get 5. And the answer is root of 5 pascals. Confirm with the calculator. Hope from your knowledge of electrostatics, you can explain why thunder and lightning occur. It has just struck here and shook my car. I thought the earth was crashing into it. Kaichweda, is that the answer?
Yes.
Okay. So the remaining part here, there are some numbers I will have to go and they're at school, I'll send them. Then there is an experiment here of determining to show the variation of surface tension with. Hey, guys, did you hear that? I'm even worried because I'm using electromagnetic radiation. You never know, it might be conductive to come to us here, but it was really strange. I don't know whether you guys have also experienced it in your areas, but it was really quite a heavy blast of the thunder. Wow. With a very big spark. But the good thing we know physics explains that if you see the spark, you're safe. It has already gone. So by the time the sound comes, though we have that question which is common, explain why sound is one illustration as to why sound travels slower than light, or why light travels faster than sound. I think you'll discuss that a lot in waves. Fatma, everything is physics. If you can't see the physics around, then you don't know what you're dealing with. Even you being there, being alive, physics can explain everything apart from God. You can even explain evil spirits. So we need to know those items very well. But anyway, I was still mentioning that we are going to, there's an experiment I'm going to send. I'll put it both on my Google Class and the WhatsApp group. It's about variation of surface tension with temperature using the jiggers method. And you'll see that right up. In case you get a challenge, I'll take you through again and have a better write-up for that. But with that, I am happy to announce that we are done with fluid mechanics, the whole of fluid mechanics in advanced level physics. So whoever has not missed a single lesson, just do one thing, solve as many numbers as possible, because at least they can bring 2 numbers or 1.5 in mechanics concerning fluid mechanics. So we shall go back and deal with other aspects of physics. I'm going to go back to heat, and we do some work in heat up to some, so that we have some drive also there. Then because we have 2 days, I'm also looking at adjusting one day to go in for heat, the other day to go in for modern. I'll see how best I can handle that. Then the reason why I wanted that is because I'm looking at a point of not being able to, or making one side be a little bit less covered and the other side be greatly covered. So I want to minimize that. And one way we can do that is by having at least every session tried out. And that's, I can do it by doing on one day heat, on one day modern physics. Okay? So, any questions in fluid mechanics? The numbers I sent have questions on fluid mechanics. Please, now you are capable of answering all the fluid mechanics questions you land on. All of them. So you should be able to answer all those fluid mechanics questions. I'm going to upload more seminar questions on my Google Class so that you can also be able to go and try them out. But like I've said, try out all those numbers in the areas we have done. When you get a challenge, post it on the group or post it on my WhatsApp so that I can be of help or someone can be of help. Right? So starting, but I think, let me do this, guys. How do you see if I organize a test and I post it on my Google Class? I think it will also be helpful. Ah! Never experienced this kind of writing. Sorry guys, I have some guys in the car. Now when they are scared, me I'm a physicist, so I'm a little bit comfortable, but for them they are a hell way scared. So, you know, apologies for some of the stimuli we are experiencing here. Yeah, I was of the view, I set a fully, like around how many numbers? 3, 4 numbers test on fluid mechanics. You guys are not men, I can mark you. Then we post it. We can give ourselves time from today. If I post the paper tomorrow or Friday, I'll give you the time from then, like up to Wednesday. Then Wednesday, we mark our tests for everyone. You post your work, like I'm going to post the test, and then we see how best we are doing in fluid mechanics. I think that's a good idea. How do you see that, guys? Those who have not been studying, those are your problems. But I can acquire you with all the notes. We have always been posting notes and asking people to write them down. Some of those of Gombe have their books with notes. We are just adding in what we have been discussing. So I trust you're ready for the test. Aren't you? Guys, when I talk about a test, people go quiet. You go mute. Unmute and talk about the test. Should I post the test? If not, I don't put my energy in making you one. Yeah?
Teacher, it's okay.
Okay. So let's see. Remind me if I've not posted it by Friday. Right? It will be purely fluid mechanics. Eh? Okay, so we can
Okay.
stop because our topic is done. So next time we shall embark on heat. Though I need someone to remind me in the group where we had stopped in heat, so that I can see where I can pick up from. Okay, then we can have a very good afternoon and a very lovely evening. We shall not have an extra lesson tonight. I think there's chemistry. So see you then.